Okay, how's my sound? I went and reverted the changes that I made to my microphone um, last stream. So we should have fewer pops. Okay. How's my sound? Went and reverted. Okay. Fantastic. All right. Today we are going to finish up with rendering models, hopefully. I'm hoping by the end of the stream we will have a teapot on screen. But a fair bit of stuff we need to do to get to there. Once we have it rendering, I want to go in and fix the issue with vertex duplication. So right now our index buffer is just identity, and that's not very useful. Then we will probably discover at that point that we need a depth buffer, because otherwise we're going to run over artifacts. So we may get that set up. And then if somehow we finish all of this and have some time left over, we'll do some basic shading. Nothing huge, but it'd be nice to get shaded teapot rather than just something with arbitrary colors on it. So offline, I went and wrote up the vector2 type so we can actually handle UVs now. Also, in our vertex shader, we're taking in this vertex data struct rather than different streams per attribute. For the sake of simplicity, I want to handle it this way. This is not the most efficient way to do this, particularly when you get into the context of a full renderer. You need to support shadow rendering and a G-buffer rendering with the same materials, and basically we'll undo this later, but for the simplicity of getting things running, having these be in an array of structs rather than a struct of arrays is going to be simpler. So we're going to have we'll have vertex data t, say position, normal, and a texture coordinate. So instead of separate arrays, we will have an array of vertices. Which means that we have to change how we're handling the loading slightly. Oh, okay. I was wondering about this last time, but I think what's happening is static analysis is unhappy because Kellogg can return a null pointer. There's not a whole lot we can do in that case because, generally speaking, standard library allocation stuff returns null when you run out of memory. At that point, well, there's not a whole lot you can do. So we'll just assert that we get a valid pointer back, and that checks it up. Okay. Make sure that I haven't missed anything. Seems like no. So this structure is actually not great. So on some hardware, particularly on NVIDIA hardware, you want to be accessing structured buffers at 16-byte aligned addresses. Which I guess now that I think about it, this is, right? That's 8 floats. Never mind. Okay, this is actually better than it was before. So sometimes you can end up having to like pad out your position and normal to vectors just because if you get the alignment correct, then you play nicer with the cache lines on NVIDIA hardware. But it looks like we are actually the perfect size right now. So this should be just 2 cache lines. Fantastic. So what do we actually need to do here? We need to, on the shader side, we're not doing everything we need to here. It's actually out to sort of. We're defining a bunch of inputs, but in HLSL, inputs are mapped to a register, which is not really a thing on actual modern GPUs. I mean, registers exist, but like the concept of there being hardware registers where textures go in this register set and buffers go in this register set, or not, it's not actually a thing. But that's the model that pretty much all graphics APIs expose in one way or another. So, if we don't explicitly assign register bindings to our buffers, the compiler will automatically assign those. And we can get those automatic assignments out using reflection, but that's kind of complicated. Like, we have to actually get the reflection data and figure out how to parse it and all of that. And there's an additional issue that you may want to have like multiple different vertex shaders that that have different resources bound. Like maybe you have a vertex shader for skinned meshes and a vertex shader for unskinned meshes, and the vertex shader for unskinned meshes doesn't actually need to have a binding for what's the word? The skinning matrices. So if we allow automatic register assignment, we will get different sets of bindings. We'll get a different layout of bindings between the skinned and unskinned vertex shaders, which in turn means that we would have to change our root signature between those two cases. That's not great. Anywhere you can share a root signature across multiple draws in sequence is good. Like if you're, we can't necessarily say, oh, we're going to render all the skinned meshes up front and all of the unskinned meshes afterwards. Because if you're having to do depth ordering for translucency or just to get early depth rejection, then you're going to interleave them somewhat. So by explicitly setting what bindings to use for each buffer, we can basically force these layouts to be more or less compatible with each other. And then the unskinned version just doesn't look at the skinning buffers. Hopefully that made some amount of sense. So the syntax for this is we give it a register and we give it a register and optionally a register space, which is right. You might have cases where you have an array of bindings for textures and another array of bindings for textures, and you want to ensure that they don't end up pointing to the same textures. Like you don't want those ranges to alias with each other. So you could manually offset the registers based on the size of the array, but when you do things like bindless resource management, you can end up with arrays of textures that are unbounded. Like there's no explicit size of the shader. So you can't just say, oh, well, the next array starts at 500 in. That's not something you can do if you don't have a fixed size. So instead you can specify space, which will say that you have two T0 bindings if you have T0 in space 0 and T0 in space 1, they'll bind differently. Right now, we're not doing anything that complicated, so we can just use the implicit space 0 on everything, but that's a possibility. We also have these logical spaces for different types of resources. So you have T, that is for textures or storage buffers of various kinds. Right? Anything that's bound with an SRD is in the T register space. And S for samplers, U for UAVs, and B for constant buffers, because constant buffers are different from shader resources used for for reasons that make sense on some hardware but not others. So yeah, so we're going to go in and explicitly assign a register to all of our types, or all of our bindings, I guess. Because then we don't have to do any reflection, and we can just build a script table on the CPU side that matches what, or rather, we can build a root signature that matches what we expect in the shader. So we will say that vertex data gets to 0. This is actually an outdated way to do constant buffers. So we will come back and change that in a moment. But for now, we'll just give it B0. And I think that's the extent of our bindings. So if we run, it seems that shader compiled cleanly, so we did that correctly. So the C buffer syntax for constant buffers is actually the old way of handling things. It's kind of ugly for a variety of reasons, namely that like all of these values get dropped into the global namespace rather than being indexable off of the constant buffer itself, which not fantastic. So in more recent HLSL, I think shader model 5, if I remember correctly, you define a struct, call this camera data, and then the constant buffer of that struct type. So this will be cleaner because it will namespace like these values, which, I mean, it just means that I'm going to have to add extra text here. So I guess in this particular case, it's not making things cleaner, but not having to deal with namespace collisions between various constant buffers would be useful. I also really don't like naming matrices this way. How we really want to name this is we name matrices based on the space they convert to and the space they convert from. That is, like, it is a incredibly useful, debugging aid, because if you ever see that you are like multiplying two matrices where the inner space doesn't match up, well, there's your bug, right? Like you're multiplying the wrong matrices together. So like if I multiplied clip from view against world from object, for example, right? Well, that's wrong. That's only correct in the case where, the view matrix is identity, which, to be fair, in this case it is, because we don't have the full camera setup yet. But that's something we can know is wrong. So like here, we have local position, which we pulled out of the vertex buffer, and multiplying by clip from view. Hey, look back, local position and view space just don't match up. So for now, we're going to ignore this. We're going to pretend that all of our vertex buffer positions are actually in view space. They are not, but we'll deal with actual camera stuff at a later date, probably. Okay. Let's double check this still compiles. Seems like it does. Okay. I think that's the extent of our shader side work for now. Okay, I get to check something off. Now we get to the tricky part, which is dealing with root signatures and descriptor tables. So a root signature is a structure that tells us how to bind things to the shader. Or rather, it describes, you have a set of registers on the shader side, either defined or implicit, and you have, on the CPU side, you have tables of descriptors, and the root signature is a way of mapping your descriptors to the actual to the actual registers. So it's like a layout for the descriptor bindings. I shouldn't really be using descriptor tables there explicitly because you can bind from descriptor set tables. You can also put descriptors directly in there. And then in addition to that, you can also put constants directly into the root signature. We're not going to do that right now. It may make sense in the future for like the vertex data binding to be part of the, to be like an explicit descriptor in the root signature, just because that gets rid of one layer of indirection in the process of loading our vertex data, which is probably a hot path for vertex shading. Okay, so we already have a place where we are creating a root signature. However, at the moment, we're creating a null one. We're creating a null one because the triangle that we are rendering right now doesn't take any bindings. So it doesn't need any bindings. We don't tell it that any bindings exist. An interesting thing, though, is that I am fairly certain we can fill out this root signature with a bunch of bindings, and then the triangle shader, which ignores everything, will still run fine with that root signature. Like the root signature is the set of things you are allowed to read rather than the set of things you need to read, is my understanding of it. I will be perfectly honest, I am so much more comfortable with the Vulkan side of things that I don't really have my head wrapped around root signatures. So this may actually be a garbage fire when we get through it. But that's what all of this is about. So the descriptor, or the root signature, is a list, more or less, of root parameters. And root parameters are either describing a descriptor table that can be bound, or a constant that will be injected directly, like descriptor that will be directly bound. We can also control the visibility of each of these parameters. So in most shading models, for example, you don't actually care about your vertex data in the pixel shader. So you can say, okay, this is my vertex data buffer. I'm going to lock its visibility only to the vertex shader. Pixel shader can't see it. On some hardware, particularly on AMD hardware with GCN, that's actually a really big deal. Because every binding you provide to the shader on, or to a shader on AMD, at least since GCN, allocates some number of scalar registers. And while you generally have less pressure on your scalar registers than you do on your vector registers, you can very easily get into a position where, okay, you're binding way too many textures that are visible to everything, and so like your shader is SGPR bound, and you'll never get the amount of GPU occupancy you really want. So general rule, make your parameter visibility as limited as possible, so that you don't pay the cost of bindings for stages that don't need them. So we're going to need descriptor tables. I mean, honestly, this is kind of overkill. We could get away with explicit descriptors, or like root descriptors. But figuring out the descriptor table stuff will help us later. So descriptor table has a descriptor range. Okay. So I think these are things we need to build. So we will start by building descriptor ranges. Constant buffer view. And number of descriptors is 1. Shader register 0. Space is also 0. Let's do that. Then we need another one for vertex data. This is SRV Can we have one descriptor? Base register for both of these is 0. Okay. So now I believe, yeah, we're allowed to put constant buffer views and shader resource views in the same descriptor table. So I think we're going to do that, because then we only have one root parameter that we have to provide to the root signature. Except the longer term, you probably want the fragment or the pixel shader to have access to the camera constants. Well, we'll do one parameter for now and reorganize this later. So descriptor table. This descriptor table has one range in it. No, that's two ranges. All right. Data visibility. Vertex shader only. So now we have one parameter. That is don't care about static samplers right now. Do we care about flags here? What are these flags again? We do not want input assembler. Like this will turn off vertex buffers if we don't include it, but we'll still get index buffers, even though that also goes through input assembler. Interesting. We can also, in addition to controlling visibility per parameter, we can also just overall deny visibility to certain stages. I'm not sure how useful that is. No. And we're not doing bind lists, so we don't care about that part. All right. So I think this should be workable. And I think this will actually still work for the existing triangle shaper. So let's double check that I'm not wrong about that. Oh, it failed to serialize. Why did it fail to serialize? Yeah, one parameter, point to that parameter. Okay, so it's a descriptor table. That's fine. Let's pointer to. Oh. Okay. You know, one of these days I will learn that like copying and pasting isn't worth it. Okay, fantastic. So this still does run. Without any complaints, so that's pretty cool. Now we need to so we have these, but if we go ahead and try to render, well, we haven't bound anything to these slots, so it's going to be unhappy. So we need to allocate descriptors, and we also need to allocate the buffers themselves to put this data in. We're going to do that down here after we build the pipeline state. We need descriptor heaps. Now, there is actually a feature flag we can check that will tell us whether we are allowed to put descriptors of different types in the same table, or like in the same heap. So if you have tier 2 or tier 3, something like that. One of the tiers allows you to say, hey, I have constant buffers and textures and whatever. Let me allocate them all from the same heap. But not all hardware that is DX12 capable actually allows that. I'm not actually sure which ones don't. I think that like early GCN doesn't support it, and possibly some NVIDIA stuff, but I don't know off the top of my head. So that implies that we really need to be creating a different heap for our constant buffer and for our prefix data buffer, which is fine. Yeah, we have tier 1, which can only support resources from a single resource category, or it can support tier 2, it can support from all 3 categories. Oh, I was misremembering. Never mind. We can always allocate buffers from the same descriptor heap. It's buffers versus textures versus render targets that are different. Okay. Well, that makes things simpler. So we will just have a descriptor heap for buffers. Maybe create a heap up here. And I know I just said that I'm going to learn about not doing copy and paste, but some other day. So we can allocate all of our buffers on a single heap. Actually, a bit of an interesting question. I don't know if index buffers also are, if they're bound by descriptors or if they're just bound as resources directly. I'll go double check that. Supposed to be like IA set index buffer. Okay, yeah, so an index buffer view is not a descriptor. That makes sense. So we don't have to worry about that. Right now we have 2 buffers. So we'll just create a heap for 2 buffers. realistically, we would create something like 64 descriptors and then do and then allocate descriptors out of that. Actually, probably not 64. We probably do like 4K or something here. Because you can end up with quite a few buffer and texture descriptors. But we don't need two for now, so we're going to create two. Next, we need to create resources for our vertex data buffer and the camera data buffer and so on. Hmm. I suspect that this is not the most efficient way to handle things, especially for constant buffers. I expect you probably want to have a big heap that you allocate constant buffers out of, but this looks like the simple way to do things, so we're going to do it this way for now. So we need these. Let's actually figure out what all of these things are correctly. Heap properties. Right. So the correct way to deal with shader visible resources in most cases is you create a resource in a GPU visible heap that the CPU doesn't have write access to. I mean, it usually doesn't have read access either, but the important thing is it doesn't have write access. And then you create some number of upload buffers that do have CPU access. So then you can write your data to the upload buffer, which will DMA the memory to the GPU. And then on the GPU, you can then copy from that upload buffer to the GPU heap buffer, which is not visible to the CPU. This is most of memory on a GPU. Like, very little memory is actually accessible for uploading on most cards. The exception being like an integrated CPU or a console with unified memory, where memory is memory, and you can generally write directly to GPU visible memory from the CPU. But for today, since I want to get this done at some point, we're going to go for the upload heap and just know that that's not the correct way to handle this. So probably going to share these heap properties against all of our resources. Just for simplicity's sake. So we're going to make our upload write combined. So write combined memory is memory that is mapped but uncached. This is more efficient for cases where you are only writing to memory. Because the CPU knows that it's not in a cache, it can buffer writes for some amount of time, and therefore write larger amounts of memory at one time. Because it knows that you are not going to be able to read back in the middle of a write. The downside to write combined memory is what happens if you do read back. So if you do actually read back from write combined memory, what happens is all of your writes flush, and then the read is uncached, which is extremely slow. So this is actually a trap that is easy to fall into with constant buffers, where you write a matrix into a constant buffer, and then you read that matrix back to multiply it into another matrix to write into a constant buffer. Well, now you've broken your write combine, and you've got this, 64-byte read that is going to be very slow. So basically, if memory is write combined, it is faster to write to, or, well, you'll get more bandwidth writing to it. But it is basically write-only. You should treat it as write-only, at least. In our case, since we're just going to put these things on the GPU and be done with it, write combined is the correct thing. The alternative, of course, is write back, which is when I write to this memory, I want you to write the value I wrote back to the cache and keep the cache in sync with the actual memory, which makes it faster to read back from the memory if you need to, but means that the CPU can't buffer those writes because it needs to keep the cache in sync. I believe I explained that correctly. I'm sure that people who know more about hardware will be screaming at the screen right now. Okay. So, rifle. Can I provide a name here? I'm going to call this unknown because I don't actually. I am pretty sure that we are not on a UMA device, but I feel like I would have to check that somewhere for that to be correct, and I don't know where to check that. I don't feel like going and figuring it out right now. And we don't care about name masks because we are I believe we don't care. Yeah. We use a single GPU, so we don't care about like managing heaps on different GPUs. That's not something I'm interested in right now. Okay, so I think that's all of our heap properties. I need heap flags. share the share it so cross processes. Okay. Buffer. Pointer. Oh, because no. All right. Buffer alignment. Actually want this to be 16 because our things are already 16, and that's cache on various things. I think technically structured buffers are required to have an alignment of 4 at least, but 16 will also be aligned to 4. So these. vertex data. Um, Structured buffers are actually required to be format unknown. Not entirely sure why, but I guess because it's a user-defined struct, there's no way that the GPU could know how to interpret that in a sort of fixed way. Really feel like a lot of this is texture exclusive stuff. Um, don't think we actually need any of these. Okay. I think the best. Yeah, that's what I thought. visible. Okay. So we actually have to do pretty much the same thing 2 more times. So this is our vertex data. We need our index data in a buffer as well. Even if we're not going to put it in a descriptor heap, we need it in a buffer. And then we need our constant buffer data. So I actually don't know if we're supposed to set a format here for index buffers. I would assume not. I assume that a view for index buffers tells us what type they are, but we'll see. But in the future, we will probably want to generate index buffers from the GPU so that we can do things like per triangle calling to generate a new index buffer that doesn't contain any backfacing or occluded triangles in it, so that we don't have to feed any of those to the rasterizer and waste effort. So if we were doing that, then we would kind of need this to be accessible as a UAV, and therefore we would need to know its type. But I think for just finding an index buffer, we don't actually care about the type itself. And same subjects here. It's bad. Okay. And finally, we need to have our camera data actually want to have this in a CPU side struct so that we can just upload an entire struct, because that would be easier. I'm still getting used to this keyboard and like having keys that are pressed in tighter than I am used to. So I keep hitting like page up and down, and various other things, and just it bothers me. So I do actually have a mat4f class, or well, struct. But GPU side, we talked about this as just row vectors. So I'm going to keep up the convention of row vectors here. Just to avoid any possibility of mismatch between them. This is okay, so now I need to actually create the first stuff. That's a lot of typing, and I don't know if I got it right. So let's run and see if things can fun. They do. Of course they do. Okay, I misunderstood. So we can't actually say that we want an upload heap and a try combine. It will give us one because uploading is wants write combined memory, but by virtue of saying, "Hey, give me an upload heap," it's the API will determine internally what sort of page properties we get. So this should be more correct. Okay. A little weird to me. Okay. Sure. Interesting. Okay, fair enough. Um, I guess because we're creating a heap with this, it has to be aligned to a heap boundary. I mean, it's definitely going to give us more alignment than we requested here, so go for it. Okay, buffers have to be in row major layout. That makes sense. See, this is why we got the debug layer turned on, because having something validate your API calls and tell you exactly what value you got wrong is so much better than just staring at H results that say, you gave me the wrong argument. Because these things take structures that have 20 fields in them, and what argument got wrong was wrong, or whatever, right? So having the debug layer is a huge help. It is also a huge help in Vulkan. If you ever want to learn how to do Vulkan, you should turn on the validator first, because it will tell you everything you get wrong. Well, not everything, but they're getting close. Definitely all of your API usage. So okay, is that everything? Nope. Hmm. A bit confused how you're supposed to upload data if it's required to be in a read state once you create it. Maybe D3D12 doesn't care about resource state for CPU writes. That seems weird. All right. We have created all of our buffers. So now we should go to data in these buffers. Okay. Not entirely clear how we actually upload to this. I think that may have to be in a command list. What am I talking about? That's not what I need to do. I need to map the resource. Nice. So we map the resource, we write to the resource, and then we unmap the resource. Actually, in practice, what you usually do with upload buffers is you will map the resource and then leave it mapped. Because that means that you don't have to bother with unmapping and mapping and unmapping and mapping, right? When you write to this multiple times. I think because these are buffers, I think we can just map this and memcopy to it. Interesting. Okay, maybe I am incorrect. But usually for like constant buffers, you want to keep them mapped so that you can write to them, because a tiny amount of data that, like, the shuffling around of pointers, like the mapping and unmapping is not free, and you probably have lots of constant buffers. Yeah. Yeah, here we go. Persistent mapping. It's just map the resource, leave it mapped forever. Okay. So most of these we actually don't want to stay mapped. Like the index buffer and vertex buffer, like, who cares? Though in practice we would actually want these to be not visible on the upload heap. So there will be a copy in between. We have our upload buffer be consistently mapped. But I think for now all we need to do is maybe I'd say no, can't just say mapping title. Okay. There. And then we will do a num copy. Let's do that now. Teapot. Vertices. Just to avoid making any mistakes here, I'm going to put these in a scope. do the same thing here. Except we have to create the camera data first. In practice, we would probably do this per frame, but we're not going to have a camera that moves right now, so it doesn't matter. Don't remember if I made the inverse optional. No, it's not optional. Whatever, we'll need it eventually. We need a vertical off of B, we'll say it's 90. That is let's make this over height or height over width. I think it's within height. All right, so a bit of an aside. We're doing some interesting things with our projection matrix. So probably the most interesting is it has an infinite far plane, and we reverse the depth buffer so that so we reverse clips VC so that the near plane is at 1, and the far plane, so like infinitely far away, is 0. This has some really interesting properties in combination with floating point depth buffers, which is by reversing that range, so when you do a perspective divide, you compact some amount of space towards 0. Because you get a nonlinear curve on your depth. Usually, you end up with that compacted, like that really high precision right in front of the camera, where it's not very useful because right in front of the camera is where you have like, the most perspective working, like right in front of the camera is not where you need precision. You already have plenty of precision right in front of the camera. So the normal forward Z buffer loses precision over distance. So you end up with issues with, let's say, sea fighting. You would see in old games all the time, where often the distance two triangles would resolve to the same depth and flicker back and forth. With reverse C, we say, okay, we'll take the precision hit close to 0 because that's close to the camera, and because of the warping on post-projective depth, that's not what we need, the precision. And it gives you more precision in the far distance. And so the two nonlinear curves between the warping and floating point precision, which is also higher near 0 than it is at 1, balance each other out, and it gives you very consistent depth precision across the entire range. And so by taking that reverse buffer and stretching it out so that the far plane is at infinity, a bunch of your math falls out of your projection matrix, and you sort of maximize your depth precision just in general. You could still improve it further by pushing out your near plane further, but in general, like, reverse C infinite far plane is the correct way to set up a projection matrix, because it just makes better use of your depth buffer precision. The exception is if you're going to render to like 16-bit depth for shadow maps or something, then it becomes less important, because integer buffers don't get the benefits of reverse C by virtue of not having, like, they have uniform precision across all values. So there's no point to flipping the warp direction. That said, usually I will flip my ortho cameras as well, just because even when you're rendering to UNORM, it doesn't get significantly worse. And then you have a consistent model of clip-spaced depth across all cameras in your scene. Okay, that was a long-winded explanation. You can Google this. Many people have written blogs about why this is a cool thing to do. The other thing that we do is, you'll notice that this doesn't just make a perspective matrix, it also makes the inverse of that matrix. This is a pet peeve of mine, is that people will compute a perspective matrix and then feed it through a generic inverse function to get their inverse projection matrix. And that is terrible. It's terrible for two reasons. One is computing the inverse analytically is really easy. Like, this is not a lot of work. This is definitely less work than doing a 4x4 matrix inverse. More importantly, most people implement matrix invert as the adjunct divided by the determinant, and that works more or less, but you lose a lot of precision. just by virtue of you're doing a huge amount of math on all of your matrix values in floating point. So unless you're going to double for your matrix inverse, which makes it not fast anymore, you're going to lose precision. So the point is, like, when you have something that is creating a matrix that is going to be relatively sparse, like a projection matrix or a view matrix, or things that you can reasonably determine a cheaper symbolic inverse for, you should do that work, because, like, I worked this one out by hand. You don't actually have to do that. You can throw this problem at, like, Wolfram Alpha, and it will tell you what the correct thing to do is, and as a result, you will get a much more high precision you'll get a high precision inverse, and you will not, like, you won't spend, like, you won't waste all of your, you will get higher precision, and it will be cheaper. Okay, I'm off my soapbox now. I've had my rant. So this will make us a perspective matrix. I then need to build the actual camera data structure. So we will pull out the rows of our projection. And all right, so now okay. Seems to. So let's I am going to take a couple-minute break to refill my drink, and then I will be back, and we will push through and see if we can get to actually rendering this in the next half hour or so. I will be Okay. This is wrong. That would have been not very much fun to debug. All right, so to set the index buffer, we need an index buffer view. Which takes the location, which is the index buffer's GPU pointer. Format, which is posted. I think we should set it as R16 event. It may want R16 typeless, but UN makes more sense to me. Just needs that size. Geez. And list for all instanced. Count on instance. Start at 0. Start at 0. Start at 0. So we also need to scripted table or something. need to set script heap as well. So we need to create a descriptors table. No. Okay. What I need to do here. I think I need to actually create script table. It's just a descriptor. It's roughly no, apparently not. correctly. GPU descriptor handle. Okay, so our descriptor heap needs to allocate both no, that doesn't make sense. Right. Okay. I understand now. So descriptor tables aren't actually an object you create for like runtime systems. It's just for the root table, and then you set the base descriptor, and it's assumed that there is a contiguous range of descriptors. That makes sense. Okay. Let's see. I have this descriptor heap, and it's really should down here where I can actually use it. Okay, this is getting a little out of hand. I need to factor some of this into functions and structures rather than having all of these things in main, but we'll get to that in a bit. Well, we probably actually won't get to that today. We will get to that next time. I just want to push through and get something that is actually useful. It's creating a survey. State buffer. This needs a CPU handle. I assume these are like aligned with each other. So like I think if you have like an SRV and the constant buffer view in CPU handles, then like get the GPU handles for that. I think that's what's going on. Or am I completely missing a step where we have to build a scripting table and copy it to the GPU? Okay. Yeah. I'm going to assume that's how it works. If it doesn't, well. Eventually, that's complicated descriptors. I don't know. I know it will be useful in the long run to have done all of this, but this feels like way too much interaction. Mm. Still needs to be unknown because it's a structured buffer, I'm pretty sure. Um, oh, that's a lot simpler. think what we actually do here is now we say the descriptor heap, get the handle for heap start. And then because these are contiguous in that heap, this should work. So, is there anything else we need to do? We change the pipeline state at all. Yes, we have to change the shaders. Right? Something. Oh. Ah, okay. Uh, so there's a lot of. We really should be like querying. For like minimum sizes and such for different types. But fair enough. Yeah, I am missing a step here, aren't I? Okay, well, it could be worse. Um, well, we do have RenderDoc open, so let's see if it. Hmm. Okay, well, that's not great. We will have to debug this the hard way. So, gives you a thing to test is, do we have our winding order backwards? Seems like no. We are probably um, probably inside of it. So if backface calling is on, oh no, central calling mode should have made it visible. Let's push this out 10 units just to see them. Okay. And if we go the other way, no. Without RenderDoc, this is going to be really obnoxious to debug. seemed to be an API usage problem. Because if it was, then I would expect the debug layer to be yelling at me. So that kind of suggests it's a shader problem or a data problem. So one of the possibilities is I might be misunderstanding how these heaps work. I suspect it's behind us. Maybe doing this will be it. No. Okay. Okay. My guess is either there's something wrong with our data upload, or there's something wrong with our descriptor binding. But I'm not sure what we're doing wrong. I think I'm going to go ahead and end the stream here. Didn't get quite as far as I wanted to today. I wanted to get to 500, but I have no idea what's going on with our descriptors, and I think what I need to do is go and read about this. That's going to be real boring to watch on screen. So maybe next weekend I will come back and I don't know, at that point we may actually be able to run the mesh, and then we will be able to come in and clean up this code, because it's getting a bit grody. But I think that's it for today. See you next time.